All right, it's 4 o'clock. Let's go ahead and get started. Okay, so a bunch of big announcements, I guess. Number one, your final will be take home, and I'm gonna give it to you on Wednesday, and you're gonna have probably either Monday. I think I'll probably have you turn it on that Monday, but I'll let you know on Wednesday, the following Monday, and you're gonna have to add. I'm not gonna tell you what it is yet, but you're gonna have a few days to do it, and it's not that difficult, right? Okay, and mostly will be on this array section, so it probably won't be cumulative, right? But that I think that's the best way for you to really understand or to really learn the material. You got to put it to use. So I think that's the best way to make an example for this array-based section. All right. Okay, that's the first thing. The second thing is you have your homework due on Wednesday, and your final will build off of that. So make sure you do that right. All right. And we'll talk about that today on how to calculate, or how to do that correctly, or at least how I did it. All right? Okay, so today's lecture, and one more thing. The Green's function chapter, I think we're going to omit because we've covered too much in this class. And what we're going to do instead is do a bunch of examples on how to calculate GTD and how to do this array-based stuff so that that'll be next lecture as well, so that you guys will be well equipped for your final. All right? Okay, any questions on that? Of course, you have questions, but I can't answer what the problems are until Wednesday. All right? Okay, good. All right, so what did we do last time? Okay, so today what are we going to cover? We're going to cover uniform theory of diffraction and uniform asymptotic theory. These are two corrections to the problem that we saw last time with the geometrical theory of diffraction, where the diffraction coefficients are singular at the along the shadow boundaries, right? So GTD works very well away from the shadow boundaries, but when you get to the shadow boundaries, so let me jump ahead. Remember, we did this last time. GTD works very well and recovers the exact solution far away from the shadow boundaries here, but at the shadow boundary, it predicts an infinite amplitude, right? So that's incorrect. But we're going to learn two new approaches today, which correct this problem and recover the exact series solution and the Sommerfeld solution as well. So in order to do that, we're going to jump back into the Sommerfeld solution, and we're going to revisit it, all right? So what are we solving here? We're solving the scattering of a plane wave. We have an incident plane wave here, and it's incident upon a PEC half plane. That plane extends off to plus infinity along the x-axis, and it has one edge located here at the origin, all right? So what we're going to do is we're going to calculate the electric field from x equal to minus 6 lambda to x equal to plus 6 lambda along this line, which is located at a distance of 2.25 lambda above the x-axis. All right? And we're going to compare that electric field, the total electric field, between three different kinds of solutions, three different approaches: an exact Sommerfeld solution, an exact series solution that we learned last semester, and the geometrical theory of diffraction. All right? Okay. So we have an incident plane wave here, incident at an angle alpha equal to 30 degrees. This angle is measured from the top face of the plane to the incident k vector here. So this is k incident, right? All right. And then we have our observation point, which is some point on this line, parameterized in polar coordinates. So we have a rho and a theta. All right. So let's calculate the exact Sommerfeld solution. The Sommerfeld solution we went over before, but the exact Sommerfeld solution was written in this form. We have z hat because we're talking about either the electric field, EZ polarized, in and out of the board. So this is EZ, in and out of the board is the only electric field component, and we'll plot the total electric field along this line. Or we have the incident magnetic field is Z polarized, and that takes care of the other situation, the other polarization. But we're going to construct the solution in terms of HZ, in terms of the magnetic field, and we're going to plot the magnetic field up here, all right? That way we only have to deal with one component. So this really should have sort of a vector here, because I have a vector on the right-hand side of the equality, and on the left side, I show a scalar components, right? Which is not good. So it should be a vector here. So U total is Z hat, and then we have this incident plane wave is e to the jk rho cosine phi minus alpha. I know we saw that last time, but here's how we calculate that. We have e to the ikxx plus kyy. And in this coordinate system, if you convert these variables to cylindrical coordinates, then you end up with this expression. All right? Okay. Now, since this is a plane wave traveling along, say, the plus x and plus y axes, we would expect this to be e to the minus j, but we're in the e to the minus I omega t time convention, right? So it's actually conjugated of what we're used to. All right, so for example, if let's say phi or alpha is equal to 0, right? If alpha is equal to 0 and we observe, say, along this axis as well, then also theta is equal to 0, then we just get e to the jk rho, where rho is x, which is what we expect, right? Okay. Now, we multiply that by the Fresnel function. We're going to see this a lot today in today's lecture. The Fresnel function is a function f of x, which has this form. It's e to the minus I pi over 4 over the square root of pi, integral from minus infinity to x, e to the I t squared dt. All right? Integration of a squared complex exponential, or an exponential to e to the I t squared. All right, what does that look like? We saw that last time. It looks like this. So what are the properties of this? Here's the Fresnel function. It's a function of x. That means that we plug in x, that defines the lower limit of integration, and therefore we can integrate this value once we define that x, and we get some scalar value that's a complex number. All right, so the x is a real number, but the output f of x is a complex number. And here is the plot of, in the complex plane, imaginary vertical, real part horizontal, and we have different values of x. Here's x equal to 0, for example. So if you plug in 0 here, then you get this value, which is 0.5 negative, 0 for the imaginary part and 0.5 for the real part, right? All right. Here is x equals to 3. Here's x equals to 4, and minus 3, and minus 4, and minus 2. Here's x equal to 2, right? So what's happening here? As you increase this argument x to infinity, this integral starts to converge to some point here, 0, 0, right? And if you go negative x, then if x becomes negative, here's negative 1, negative 2, negative 3, negative 4. If you go x to minus infinity, for example, then you're going to converge to 1, 0. All right, that's a very important property of this Fresnel function. So that means that it starts out at 1, and then it slowly winds down. Okay, so the absolute value, for example, winds down to 0. Looks something like that, right? But of course, this is a complex number, and it's, real imaginary part, and it's rotating in the complex plane. So it's really not just a constant like that. What it is instead is it's like an oscillation, right? Maybe it's a symmetric oscillation. And that's exactly what we see when we use this function in our solution here. So look here. The Fresnel function is oscillating, right? And then it starts to go down to 0, right? And it's because of this function that goes to 0 where you so the Fresnel function starts to decay, right? So, and we could see it starts to oscillate around a value of 1, for example, if it was just the magnetic field. So this is 1 over eta, right? But here it's a value of 1. Oscillates around that value, and then it goes down to 0, right? So it gives you the correct behavior, which Sommerfeld originally derived, of the diffracted field, all right? Okay, so Fresnel function here, and this is his derivation here. And then we have the diffracted field due to the reflected field, right? So there's an incident field here that goes like this, and there's a reflected field that can go like that, and the diffracted field go that way, right? Yeah, that's incorrect. So reflected field goes this way, incident field goes this way. We'll see that. Okay, so, and then rho, of course, in phi are parameterized exactly like that. So for the above problem, we know that alpha equals to 30 degrees, so that means alpha is pi over 6. And we can replace these alphas with pi over 6. That's what we've done here, right? Okay. All right. And then for H-pole incidence, we have something very similar, except when H-pole is incident, the electric field now, if H is Hz, the electric field's in this plane. And when the electric field's in the plane orthogonal to the edge tangent, that's called hard polarization, all right? So the H-pole incidence is modeling the hard polarization case, and that means we use the hard polarization diffraction coefficients. But in Sommerfeld solution, you switch this plus to a minus. All right. For EZ, that's soft pole. All right. So here's our exact series solution from ECE 5105. You can go back to your lecture notes from last semester to understand the solution, but here's the electric field, the total electric field for the particular problem under consideration. When alpha goes to 0, this wedge collapses into a half plane, right? Okay, so now we can do the GTD solution. We need the shadow indicators first. So first, the incident plane wave looks like this. So it lights up everything below the half plane and everything above it in this region, but all through here, it's dark, right? So it's geometrical optics, it's rays. So this is the dark region from alpha going from 0 to 30 degrees, or 0 to alpha is dark. So that gets a 1, plus 1. And when it's lit, then you get -1 for E incidence, right? Or epsilon incident. For the reflected field, the first reflected ray kind of comes off the edge like that. Let me draw it more correctly here. So you go here like that. And therefore, this is all lit, and this is all dark, right? And of course, everything above is dark. All right. So now we know our shadow indicators, and we can use our step functions to define where the incident electric field is and where the reflected electric field is. So the incident electric field will be e to the ik rho cosine theta minus pi over 6. The reflected electric field is theta plus pi over 6, and it has a minus sign here, right? Okay. Now that we have the geometrical optics solution, we can compute the diffracted field to complete the GTD solution. So here's our diffracted electric field, the formula for that. There are a few things we need to calculate. This is known. All we need to know for that is the sigma, which is the length of the ray from the diffraction point to the observation point, all right? The divergence factor we have to calculate. To calculate that, we have to calculate the radii of curvature for the diffracted wavefront. And we remember that there's only one radii of curvature for the diffracted wavefront, right? One of them is what? 0. Yeah, so I may have misspoke before. The other diffracted radius of curvature is 0 because each of these, there's a point caustic here, right? Along this line, you get a line caustic when you consider all such diffracted rays, but that line caustic has a infinite curvature and 0 radius of curvature because it's a point focus, right? Think of like when a parabolic reflector focuses to some point, then the radius of curvature there becomes infinite at that point source, right? Or at that focus. Okay. So, go ahead.
The curvature become infinite at that point?
Yeah, because think of a sphere, right? If I have a sphere, then the radius of curvature is the radius of the sphere. But as that sphere shrinks down to a point, then that radius goes to 0, and therefore 1 divided by 0 is infinity, so you get infinite curvature at the point. Okay, so this is known, right? So we just need to calculate this radius of curvature here to find the divergence factor. So to calculate the divergence factor, one of the radii we know is since the incident field is a plane wave, what's the radius of curvature of a plane wave? Infinite, right? Because a point source infinite far away generates a locally planar wavefront, or a pure plane wavefront, I guess. A locally planar, infinite radii of curvature. All right, so we know what R naught incident is. That's this piece of this, right? So what is this? This is the formula to calculate the diffracted radii of curvature. Here it says that's equal to 1 over the radius of curvature at omega I, which is the plane containing the tangent and sigma incident, right? So we know that's infinity because it's a plane wave. The second component, the second term, has the curvature of the edge, the angle theta I or beta I, which is the angle between the edge tangent. So let's go back here. Theta I or beta I is the angle here between the incident field and the tangent. Incident k vector and the tangent, right? So if what do we know? What is beta equal to? Is this beta I also equal to beta by the law of edge diffraction, right? We know that. Okay, so in this case, we're normally incident on the edge, right? Because the edge is here. This is the y-axis, this is the x-axis, and we're normally incident like this, and the edge tangent is in and out of the board, right? Say z. And that means the angle between k incident, or sigma incident, sigma hat incident, and the edge tangent is 90 degrees, right? Okay, so, all right, so that means that okay, so yeah, so we'll get to that, right? So that's what this angle is here, beta. Kappa is the curvature of the edge. And then we have k incident, k diffracted, and the normal to the curve, right? So this is all parts of the edge, right? This has all properties of the edge. And then this has properties of the incident wavefront. So the diffracted radii of curvature wavefront depends on the incident, the impinging radii of curvature, plus the shape of the edge, right? All right. We know that our diffracting edge is straight. It's an infinite half plane. So kappa is equal to 0, no curvature. So this term is 0. That means this whole thing goes to 0. This is infinity. So this goes to 0. So 1 over r 1d is equal to 0, which means that the radius of curvature of the diffracted wavefront is also infinity, right? It's a diffracted plane wave. All right. So that means if we go now to the divergence factor here, which is from here, that's equal to 1 divided by the square root of 1 plus sigma some distance divided by infinity, right? And that equals to 1. So the divergence factor for the reflected or the diffracted wavefront is equal to 1. Since our incident field is z-polarized, so that means now we figured out this term, right? Let's now work on this term next. So we know that the incident field is z-polarized and our incident rays are approaching in the xy plane. So as we just mentioned, theta incident is 90 degrees. Thus, this term becomes 1, right? All right, we did that. Now let's work on these terms, beta and alpha. So now we find the diffraction coefficients. Since here we are in the xy plane, the beta hat, which is theta hat, unit vector always points in the minus z direction. So think about this. If I have z, x, y, and my observation point is here, then the theta hat unit vector points that way, the phi hat unit vector points that way, and r points that way, right? So the way I like to think of the theta hat unit vector, have you ever seen those things like the Grim Reaper uses to cut the wheat out of the field? So it's shaped kind of like that. So if your arm is, say my elbow is the origin of the coordinate system. So if my elbow is the origin of the coordinate system, then my arm would be the, r, the length r, to the position, to the observation point. Then your hand would be the theta hat unit vector. So as you go like this, so right now r is along the z-axis. So theta is in some direction. As I change my theta angle more toward the xy plane, the theta hat unit vector, the r plus the theta hat unit vector looks like that Grim Reaper thing. So then it points negative x when it gets to the xy plane, or negative z rather. Yeah? All right. So beta hat then is theta hat, which is minus z hat. All right, so alpha is phi, and we know we can express phi in terms of the xy basis vectors if we need to, but we don't need them. All right. Now, since our incident field is given by this expression here, and we need, so now let's work on the incident field here. The incident field is, we want to express the incident field at the point of diffraction, which is rho equal to 0, right? The point of diffraction here is rho equals to 0. Okay, good. So, therefore, and I think I had a mistake on the slides last lecture about this, but at rho equal to 0, we have E theta here. So if rho equals 0, you get e to the ik 0, which is just 1. So you get E theta incident is equal to -1 because of the direction, right? The incident field is minus z polarized, right? Because the theta hat, it's theta hat, but theta hat is minus z, as we said, right? So it's -1. All right, so E incident here, which is z hat e to the ik rho cosine phi minus alpha. Z hat is minus theta incident, which is equal to minus theta incident, so, and therefore E theta incident is -1. All right. E phi incident is 0 in the plane of interest that we're in, right? Talking about EZ polarized here, so it's only a theta component. All right, the diffraction coefficients we can find now, right? So the soft diffraction coefficient, we know alpha, theta is our observation point, and we just plug in pi over 6 here, we have that. And then the hard diffraction coefficient, the only difference between soft and hard diffraction coefficients is this sign in the middle, yeah? Okay, but since alpha, which is phi hat, we know E phi incident is 0, this term is 0, so we're not even going to use the hard diffraction coefficient, which is the phi polarized diffraction coefficient, all right? Okay, so putting it all together, now if we go back here, we had this is equal to 1, we have this equals to 1, so these two things kind of drop out, and we just have this term, and we know E theta incident is -1, we know beta hat is minus theta hat, so these two minuses cancel, we just get theta hat, ds, soft diffraction coefficient, and gk of rho, which is this, all right? So let's check that on the next slide. It's exactly what we have. Here's GK and rho, and then we have ds. That's all that was left. Of course, it's theta polarized, but there's also, we indicate that here with the z. All right, the GTD solution, we add in the incident and reflected fields, and then we have HZ polarized. All right. So here we have the results. So here we're plotting the exact solution based on Sommerfeld, which uses the Fresnel functions. We're also plotting the exact series solution that we derived last semester in 5105. And we're plotting the geometrical optic solution and the GTD solution, all right? What do we observe? So first off, the geometrical optic solution starts out as 1 as we travel from -6 lambda here to +6 lambda here. We notice that there's a reflection shadow boundary, or incident shadow boundary, sorry. Incident shadow boundary here at x equal to 3.8971. You can calculate that value. So the incident field is observed everywhere along this line, but after this line in this direction, it goes to 0, right? Okay, so that's what we observe here. And the exact series solution and the Sommerfeld solution overlap. And they're here. This the red and the blue are overlapping. So, of course, Sommerfeld and the Fresnel functions and the exact series solution, they overlap. GTD now does very well away from the shadow boundary, right? But then it has a singularity. And that's one of the problems with geometrical theory diffraction is along the shadow boundaries, there's a singularity. So we're going to fix that this lecture by introducing a different technique. I've given you the code here to do all of these plots, right? So here we calculate the arguments of the Fresnel function and, rho and theta, x and y from -6 lambda to 6 lambda, and the Sommerfeld half-plane solution here, there, and then the exact series solution from last semester, geometrical optic shadow indicators, geometrical optics field, and then Keller GTD solution is here, and then you plot them all together, all right? You're going to probably use this in your, you refer to this when you do your final exam. All right, now I've come up with another example for you guys, trying to, so you can see different ways to do these calculations. So this is called Arago's spot. And basically what happens, it's a way to isolate just the diffracted field, right? Because the only thing, so here's a PEC disk, right, of radius A. And this PEC disk is illuminated by an x-directed point source of this form here, right? And there's a bunch of rays launched from this point source at the disk. The incident field is that way, right? Incident shadow boundaries. Then the reflected shadow boundaries are like this, right? So behind the plate should be completely shadow if it weren't for the accounting of diffraction, right? But each of these edges are going to diffract, and they'll all add up coherently at the observation points, right? Okay, so it's a way to isolate just the diffracted field component. We want to calculate just the diffracted field here, and later we're going to compare that to full wave simulation. All right, so that we can validate everything. So the edge is gamma. This is gamma, this cylindrical edge, circular edge. And the parameterization of the edge is a circle. And if you take the first derivative, then you can get the edge tangent, which is phi hat. We expect that, right? If this is the xy plane, then we would expect that the edge tangent here is phi hat, right? All right. Okay, so the point source located at distance d1 from the xy plane, and the observation point at distance d2 from the disk in the, along the z-axis. All right, so here's the z-axis, here's the x-axis. So we have some incident ray here, has its coordinate system, ray fixed coordinate system, sigma, beta, and alpha. And we're gonna, since the incident field is from a point source, what kind of wavefront is it? Spherical. So every point's umbilic, it has the same curvature everywhere, and that means we can direct our principal curvatures or principal directions in any direction we want. So we're just going to use the natural theta and phi components from the actual point source like this, right? Okay, so we have to calculate the total field at z equal to d2. And the total field there is only the diffracted field. So here's our diffracted field formula. All we have to do is find all the components of it. So let's start. Compute the curvature of the diffracted wavefront, right? So R naught incident is the radius of curvature of the incident wavefront at the point O. So let's pick this point, for example. At the point O in the plane through the tangent and sigma incident, right? So here's sigma incident, like that. And at this point, the tangent is, okay, so let's do this. If we're looking at this thing on the side, so here's side on. So here is sigma incident hat, and the tangent at this point is coming out of the board, phi hat, which is equal to t hat, right? So the plane containing these two things is the xz plane, right? No, the yz plane, because neither of these things. Okay, so it's a plane that contains the tangent, which is in and out of the board, plus this phi incident vector. So it's a plane like this, right? That cuts through like that. What is the radius of curvature in that plane, right? So radius of curvature in that plane, obviously for a incident wavefront that's spherical, it's umbilic. Therefore, the radius of curvature is the radius of the sphere that goes from this point through that, right? Which is nothing but this ray. And that is square root of d1 squared plus a squared. So this is d1 squared here, and this is a squared. So this distance, L1 for example, is d1 squared plus a squared, yeah? Since the edge is the circumference of a circular disk, the edge curvature kappa, we can easily calculate that. That's 1 over a, right? 1 over the radius of the disk. And the normal to this curve is always pointed toward the center, right? To the origin of the, it's always pointed toward the origin, and it lies in the xy plane, so it's minus rho hat. Okay, now, sigma incident here, this unit vector, since we're in this coordinate system where this is z and this is x, is just the unit vector r hat with the incident angles, theta incident, phi incident, spherical angles of incidence, right? Okay. All right, now sigma incident is orthogonal to the edge tangent. So here's sigma incident. As we just saw, this is sigma incident, and edge tangent is coming out of the board there. So they're orthogonal. So the angle between them is 90 degrees. So that means beta incident is 90 degrees, and that we'll need later. And sigma diffracted now is this vector here, right? Sigma diffracted. That vector, if you translate it to the origin, is like that, right? But that we can also write in the spherical coordinate system. So we just say sigma hat is r hat diffracted, so it has its own angles, right? Okay, good. All right, what is the diffracted angle here? Well, it's the inverse tangent of a over d2. So here's some diffracted, right? Sigma diffracted. And the angle theta here is the inverse tangent of, okay, so this should really go to this point, right? So this angle here is, let me clean it up. So here, this angle goes to there, right? So here, this theta diffracted is, this is going to be A, right? And this is D2. So it's inverse tangent of A over D2. And the thing about the phi diffracted now, if I have an incident field coming this way, so that means it looks like this when you translate it back to the origin, and the diffracted ray goes that way, and if you translate it back goes that way, then the phi unit vector is always pi away from the incident one. Yeah? All right. Geometry. There's so much geometry, right? So you guys gotta sit here and go through the geometry, get good at geometry. Okay, so the diffracted radii of curvature, we have everything now, right? We just need to calculate this. We know what that is. Sigma incident. Okay, so first off, 1 over r naught incident is the 1 over r, or 1 over the incident sigma, right? Which we calculated already. The curvature kappa is 1 over a. Sine squared of beta incident is just 1 because beta incident is 90 degrees. We're coming in orthogonal to the edge tangent. Then we have sigma incident minus sigma diffracted, dotted with n. Sigma incident is this, this, and this. And then we subtract sigma diffracted, which is that, that, and that, right? Then we dot it with the n, which is minus rho hat. Okay. All right, so if you do that, then do the dot product here. This minus sign comes out. We do the dot product, we get cosine squared here. Cosine diffracted times cosine phi incident. Sine squared of phi incident, and sine of phi diffracted, sine of phi incident. As we said, phi diffracted is phi incident plus pi. So each of these you can change to phi incident plus pi, the phi diffracted. And if you do that, then you end up with, you can square this and this. And you can start to factor things out and you get this expression at the end. All right. Okay. So everybody following, or you guys are good? Questions? All right. Yeah, this just a lot of diffraction, geometry. There's formulas that you can apply, but most of this is geometrical theory diffraction, right? So it's all geometry here. Let's compute the curvature of the diffracted wavefront. So, oh my goodness. Okay. The divergence factor is like that. And we calculated what the radii of curvature is for the diffracted wavefront. So we can calculate the divergence factor now. So now we compute the diffracted coordinate system unit vectors. And you know if anything if the polarization is rotated, right? So if you come in obliquely to an edge, then the Keller cone is not opened up to a disk. And that Keller cone then has its own unit vectors that you have to rotate throughout the cone angle, or about the cone. So that's what this rotation operator does. Here's the explicit formula for it, right? So let's see. Okay, so here's the explicit formula. For our problem here, we have E naught incident dotted with the tangent, but we know the tangent is phi hat, right? We said that before. Sigma incident is the unit vector r hat in the diffracted wavefront. This is all diffracted, all right? Cross with the tangent, which is phi, and then sigma again, which is r hat diffracted. We defined that before. And then we have E naught incident dotted with T crosses sigma incident, but T is phi, and sigma incident is R incident, R hat unit vector incident. And T hat is phi, sigma is R diffracted, right? So this takes care of everything for you. Okay, so phi crossed with R is what? Phi hat crossed with R gives you theta. Very good. So this is theta hat. Now we have R cross with theta. So r cross the theta gives you phi. Very good. So that's what this phi is, right? So it makes sense, right? So for this coordinate system, it's not a cone, so we don't have to rotate anything. It's E naught incident dotted with phi hat, and that's the phi hat component. It's simple for the disk, right? But when it's a cone, it kind of changes. Then here we have phi crossed with r is what? Theta. So here's theta hat, and then we have theta E naught incident dotted theta. So it's obvious, right? So then alpha is phi, and beta is theta, right? So that's what we conclude from this. There's no rotation that's needed. Is what that means, right? All right. Good. Now the diffraction coefficients. So we have this geometry here. So here's our incident field and our incident ray. But if we extend that, then the incident angle alpha here is the angle from the top face of the diffracting edge up to the incidence k vector. And that is pi over 2. So if you put this and you start with pi over 2, and then you have this extra angle, but that extra angle is the same as this angle, right? And that angle is nothing but inverse tangent of a over d1. And then theta here is nothing but the inverse tangent of d2 over a. Now we can calculate the soft and hard diffraction coefficients. And we know alpha, now we know theta, right? All right. Now we compute the diffracted field. So here's the diffracted formula. We substitute this in for g of k, right? Oh, it's all of this, right? And then 1 over sine beta we know goes to 1. The divergence factor is here. And then we have, instead of beta and alpha, we have theta and phi. And then we have E naught theta incident and E phi incident. So this should really say, it depends on how you define this, right? Matter of fact, I've defined it down here. So really, this should not say sigma incident. This should be 0. This should be 0. All right? 0 here, 0 here. Because I've defined E naught incident at the point O, 0, to already include the phase, right? The incident phase. All right, and we calculated all these formulas, right? Okay, good. So if you add up all those diffracted rays, what's the problem with this? I wonder if any of you guys can see it. Say I want to compare this to full wave simulation. Either besides that, what's the problem with trying to calculate the field here? So what is this point here? It's a caustic, right? And what do we know about our ray-based theories? They fail at caustics, right? So this approach really can't be used to calculate the field there, right? Probably do some kind of calibration thing if you compared it to another Fourier simulation or another numerical method. But so to circumvent that problem, what I've said here is to validate the solution, we cannot compare the result with full wave since ray-based techniques fail at caustics. Instead, we can observe the diffracted field at some point off the axis and compare with CST. So here, instead of observing here, we're going to observe here instead, right? So instead of here at D2, this distance is D2, we're going to observe at A over 4, so A over 2 rather, 0 and D2. At that point, it's not a caustic, right? And at that point, we only have 2 rays that contribute, right? Since the Keller cone is always a disk. So let me show you what that looks like. The Keller cone is always a disk, right? So that means this ray diffracts in this plane, right? So there's 1 ray that goes to this point from this right edge, and 1 that goes to this from this point from the left edge. Every other part of this circle or disk that's illuminated will not collimate. The ray won't reach that point, right? Matter of fact, all these generate a ring of observations if I rotate an azimuth, right? But there are only 2 rays that go here. So we can calculate those 2 by saying diffract 1 and diffracted 2, and everything's the same. And there's some geometry here that you can go through. So you can calculate what sigma 1 is, which is this distance, which is nothing but d2 squared plus a over 2 whole squared. Sigma 2 is this distance, d2 squared plus 3a over 2 whole squared, because you have a here plus another a over 2, which is 3a over 2. Sigma incident is the same, right? And now we calculate our diffracted radii of curvature using our formula, but now we have theta 1 and 2. Theta 1 and 2 are given here. And this formula is the same as before. The incident field hasn't changed, just the observation point. And we only have hard diffraction here because in this plane, which is the xz plane, right? This is x. The xz plane, there's only theta for an x-polarized point source. So there's no phi, right? All right, so I'm working on this still to compare it to ZST. I was running simulations today, but I think I have a mistake somewhere in my MATLAB code. So I didn't get it on time, but I'll show it to you on Wednesday. All right, the Fourier simulation comparison with this. Let's extend our geometrical theory of diffraction to wedges. Before we were able to show what the diffraction coefficients are for half planes, but what about a wedge? Consider the wedge geometry shown in the figure to the right here. The wedge consists of two smooth, curved, perfectly conducting surfaces sigma 1 and sigma 2 that meet or intersect along a curved edge gamma. So here's gamma, right? All right, they're the half planes, so this is a curved edge, right? They're half planes T1 and T2, tangent at O. They're tangent at O, to sigma 1 and so the tangent to sigma 1 and sigma 2 at O. Form a planar wedge which approximates the curved wedge in the vicinity of O. The exterior angle between T1 and T2 is m pi, with m between 1 and 2, right? That's saying from last semester. Consider now the diffraction problem of the wedge being illuminated by the incident field E incident. The total field solution again consists of the geometrical optics part and the diffracted part. The geometrical optics part, EG, consists of E incident and in general 2 reflected rays, one from each face, if you illuminate both faces. So in this example, we're illuminating both faces, right? This illuminates this face, sigma 1, and illuminates this face, sigma 2, right? So here's sigma 1, here's sigma 2. We're looking at a cross section of this thing now, right? Orthogonal to the edge tangent. And we have an incident field illuminating both sigma 1 and sigma 2. So we have 2 reflected rays, right? And then we have a diffracted ray as well. So this is a curved wedge, right? But we have this plane T1 is tangent to sigma 1 at the point O. And this plane T2 is tangent to the surface sigma 2 at the point O. So this is the planar wedge approximation of our curved wedge, right? At the point of diffraction. All right. So then there's their own shadow boundaries here, depending on which reflected ray we're talking about. The reflected shadow boundary, there's 2, and we can write the general form of the geometrical optics solution as incident plus reflected 1 plus reflected 2. But you may only illuminate one face, which is the situation here, for example. So here we have the incident field illuminating only sigma 1. So here's a different kind of wedge. We have sigma 1 and then sigma 2 like that. So that's the wedge, right? And we have an incident field illuminating this. Here's our planar approximation, our planar wedge, T1, and T2 probably goes like that, but I'm not showing it. And we have some incident plane wave illuminating that. So you might only have one reflected field, right? So the diffracted field in the wedge problem may be calculated as before. The only modification needed is that the diffraction coefficient is generalized to become this. And we derived this last semester using exact series expansions, right? This is the exact same thing we derived last semester when we solved scattering from wedges. All right, these are the diffraction coefficients. And if m, I think if m is equal to m over 2, this collapses back to the half-plane solution, right? So you can go back to your old notes from last semester. So that's it. If it's a corner and not a half-plane, a sharp knife edge, if it's a corner, use these diffraction coefficients instead. That's it. And that should be intuitive because we derived these last semester, yeah? All right. Let's get to the UAT. And okay, so so we saw that the GTD theory has a problem along the shadow boundaries. It predicts infinite amplitudes, which is incorrect. So let's consider again the diffraction of an incident field, E incident, by a perfectly conducting screen sigma with edge gamma. Yeah? The total field is again given by, in the new theory, the uniform asymptotic theory. One of your homework problems is to read the paper by S.W. Lee, where we get a lot of this stuff that's in this presentation and the notes and for the course from his work. That paper you're going to read of his as part of your homework, right? Uniform asymptotic theory. So the total field in the uniform asymptotic theory is still diffracted plus geometrical optics, right? But now we're going to call the geometrical optics capital G. If you go back, you'll notice that in the original GO, we had a lowercase g. But now for the uniform asymptotic theory, we're going to modify the geometrical optics field. And when we modify, we're going to change the script or the case of the superscript to a capital letter. Okay, so E capital G now. In the UTD approach, oh, sorry, this is UAT. I'm sorry. This is not UTD. This is UAT. The diffracted field, E diffracted, is unchanged. So we don't have to do anything new to calculate the diffracted field. But the total field has changed. The geometrical optics field is modified according to the following. All we do to correct for that problem with the geometrical theory of diffraction is we modify the incident field in this theory. In the uniform theory of diffraction, which we're going to learn next, we modify the diffracted field instead of the incident field. Incident and reflected. So what do we do in UTD? Oh, sorry, UAT. We modify the incident field and the reflected field to have these kinds of coefficients. These coefficients are the Fresnel function. Okay, we'll learn what these are. They're called detour parameters. The Fresnel function evaluated at the detour parameter of the incident field minus the leading term of the asymptotic expansion of the Fresnel function, f hat. And that's the same notation we did before. First term of the asymptotic expansion of the Fresnel function. We've seen that before. And here's the Fresnel function itself. All right. So, and then these are the detour parameters. So let me come back to the detour parameters in a second here. But what I want to say is this f minus f, what is its properties? So f minus f is 0 in deep shadow. So way over here, 0. It's 1 in the lit region, and it's infinity along the shadow boundary. Exactly like the kind of like it's the Fresnel function, right? So the Fresnel function, we saw these same properties, right? So let's go to that. The Fresnel function itself has these same properties, right? In the deep shadow region, that means that we've gone all the way to this point, right? Which is here. Deep shadow is 0, right? 0 real, 0 imaginary. It's a large argument, right? Positive argument. In the lit region, deep lit, we get 1 and 0. Right? And normally the Fresnel function goes to 0.5, 1/2 at x equals to 0. But now at x equal to 0, which is going to be the shadow boundary, we're going to subtract the leading term of the asymptotic expansion, which is going to make this thing singular. All right? So let's look at that. The leading term of the asymptotic expansion. So here, the leading term of the asymptotic expansion is infinity. What are we doing that for? Because the geometrical optics field now is going to go like this, right? But then it's going to go to infinity again, and then it's going to go to 0. But this is going to be out of phase with this GTD one. It's going to cancel it, right? It has the same singularity. The GTD has the same singularity. But we're going to cancel it by subtracting it, right? So, okay, so what are the detour parameters? Well, when do we apply this thing? So the detour parameters are defined like this. The detour parameter is shadow indicator, absolute value of the square root of k into s diffracted minus k into s incident, which is the length of the ray from the observation point, the diffracted observation point to, so this one goes from the point of diffraction to the observation point, and this one goes from the source to the point of diffraction, right? And then the reflected is defined similarly. So note that the square of these detour parameters, so if you squared this, then you would not have the square root, measures the excessive ray path from the source to the observation point via the edge gamma. So here, let's say here is the edge gamma. Here is my source, point 1. Here is S incident. And here is the observation point, S reflected or diffracted. And here is the excessive path. So this is 0.3, this is 0.2, right? So the excessive path length is what this is measuring from the observation point via the edge. From the source to the observation point via the edge, how much in excess is that than the direct, right? It's known as a detour parameter of the incident field. So when the detour parameter is 0, we're at the incident shadow boundary. And when the detour parameter is greater than 0 or less than 0, we're in the shadow or lit region of the incident field. So that's the way this works, all right? It's a parameter that is 0 on the shadow boundary where we want it to be infinite. And it's very, very, it's when it's less than 0, then we're in the lit region. And when it's greater than 0, we're in the shadow region. So it's an indicator how far away you are from the shadow boundary in a sense. All right. So here are the properties of that F minus F hat. And all we're going to do is we're going to modify the geometrical optics, the incident and reflected field part, with this F minus F incident, or F hat, F minus F hat. Same with the reflected field. So we're going back to the half-plane solution that we had before, and we're going to add UAT to it, okay? So now here's the the detour parameters. And if you calculate the detour parameters, you get the following expressions, right? E incident K squared of SD minus S incident. We know that there's a common factor, and then it depends on the observation angle and what alpha is. We know alpha is pi over 6 for our half-plane solution that we've been working on. And we can calculate this parameter like that, right? The diffracted field is exactly the same as before because UAT does not modify the diffracted field, it modifies the incident field with the same singularity but opposite as the GTD has, the diffracted field. This diffracted field has this singularity, right? The incident fields, with the modification of the incident field, we're going to cancel that out. So here's all the code that I wrote to append to the other code that I gave you for making this plot. But now what have we done? We've added UAT to it, and look how perfect it is. It now recovers the exact series solution and the Sommerfeld solution. Both of these are exactly the same as UAT, so it's perfect now, right? Okay, and GO obviously is step function, and GTD has a singularity, right? So it fixes that problem. Uniform asymptotic theory. All right, what about the uniform theory of diffraction? Now, instead of modifying the geometrical optics part, oh my goodness. Instead of modifying the geometrical optics part, we're going to modify the diffracted part. So now the diffracted field has a capital D instead of a lowercase d. And the way we're going to modify the diffracted field is we're going to multiply the diffracted field by the singularity, which is in F hat, right? The leading term. So we multiply by F. Okay, so F divided by, before we had F minus F hat. Now we're doing F divided by F hat. And we take the absolute value of the detour parameters. So like this, right? So what are the properties of this ratio? It's equal to 1 when we're away from the shadow boundary, where we already know that geometrical or GTD does well away from the shadow boundary, right? And when we're on the shadow boundary, it's some finite number divided by infinity, so it goes to 0, right? Okay, good. So it kind of tames this. How can it just be taming that? Well, this is the singularity in the GTD field, right? So we're kind of multiplying it out or canceling it out. Or this ratio is, right? The ratio is. So returning to the half-plane problem, the diffractive field can now be written as, all we do is add this and this, right? In our half-plane solution. GO remains exactly the way it was before, lowercase g. Here's the code that you add to that half-plane solution problem code that I gave you, and now we've added UTD, which is the blue, and we see now that we have perfect agreement between the exact Sommerfeld, the exact series, UAT, and UTD. All right? So you can use either one.
In the previous one, we don't have a diffracted field.
Yeah, you do. In the previous one, you have diffracted field, but we keep that the way it was before. Okay. We don't modify it. We modify the GO field.
Okay.
So the GO field ends up, so the diffractive field is the same as we had before, but the GO field now has this F minus F hat, right? And now we use both, right? Now the other one, which is UTD, we modify the diffractive field and keep the GO the same as it was before. Now this is a ratio instead of a subtraction or a difference. All right? Okay. So that's it, man. We're done with the ray-based theories. That was everything that I wanted to teach you guys about that. Oh, we might add one thing, but that's just extra. It's not part of something you need to know on Wednesday, which is our last class, right? Ray-based techniques are super powerful. They're super cool. As a matter of fact, if you want to do anything with inhomogeneous media, where you have permittivity varying as a function of position, this is the only way that I know of to handle that. Maybe you could come up with some other way, of course, but this is the way I would go to as the first cut. All right? Okay, and if you want to do diffraction from like reflectors and stuff like that, then these are the things that you need. So now, is there any questions on any of this ray stuff? You won't have good questions until you go and try it, right? Until you really need to say, you know, how you understand it, write out your solutions to your homework. But then, and then when you go try to put it to practice, right? We'll get more examples on Wednesday. We'll do more diffraction examples so you'll see what you need to help you with your final. Yes?
There's a commercial software called Grasp. I'm not sure if you know it's
Yeah.
So they use you can either choose PO, GO, and with the diffraction, it was either GTD or UTD. Is there any reason why they don't use UAT or UTD?
That's a great question. I'm sure. So, okay, so maybe they're not explicitly stating that it's UAT, but maybe it's really UAT, right? A lot of people maybe you'll say GTD, but really you mean the asymptotic, the uniform theories. Or they must be explicit about that. I'd be surprised if a software package used array-based diffraction and didn't have the uniform theories. I'd be surprised. Yeah, but now at least you know what all that is, right? So when you go to use these software packages and you have all these buttons to check, you know, include diffraction or, you know, analysis approach, use PO and GO or PO and GTD and all this, then you know what it is doing now, right? So you're much more better at using the software, right? Once you know what it's doing. But I like to write my own software because then, of course, you have to debug it and it takes forever and validate it, which takes even longer. But then you really understand what you're doing. And sometimes you can handle more problems than the software quicker. You know, you can do it faster. Okay, good. So now let's talk about your homework. Yes.
Are UAT and UTD always in agreement, or is it only for like, because that was like a simple example?
That is a great question.
It was like mentioned in the paper.
That's a good question. I don't have a great answer for that based on my experience with the theories. So I'd have to maybe read up about that or read about certain situations where it doesn't. So let's see. So one of them modifies the incident and reflected field. It probably depends on where caustics and shadow boundaries are, which approach you might want to use, right? I'd have to think about that. But that's a good question. When to use which theory, right? Which one's better? Very nice. Okay, but I'll think about it and I'll let you know. All right, any other questions? Yes.
So this or this geometric optics is based on the assumption that k goes to infinity or very high frequency cases, and in the examples of geopathic ring in this slide, we are using a point source, right?
That's right.
And so what I want to ask is that when could we make an assumption that the frequency is very high so that we use geometric optics?
So it's because everything is based on localization. So we model everything in ray-based theories as we only need to trace a piece of the wavefront at a time, which means other parts of the structure, the current induced on them, don't affect what's happening locally at the point of intersection of a ray and the geometry. So we can consider one ray carrying one piece of wavefront, and reflection problems using canonical geometries that represent locally what that geometry looks like half plane or infinite sheet, at that point of reflection. Now that's valid for electrically large structures, right? You know, 10s, 20s, or hundreds of wavelengths, right? The bigger it is, the more accurate it is. Okay, so it's electrically large, right? K goes, the size of this electrical structure goes to infinity. So you can use it at lowest frequencies if you have a big reflector or something, right? But we saw that if we can't take K to infinity and K is finite, then the asymptotic expansion is still valid, except we're going to find that only a certain number of terms are useful and the rest of them we have to throw out, right? So that was when we were talking about the asymptotic asymptotic expansions.
May I ask, in the rear dual category antenna, which source this antenna use?
Point source. So we're going to illuminate with a point source,
How
right?
could it be implemented in the real world?
Okay, so point source is a model. Okay, so point source, it's an x-directed point source. So it does satisfy Maxwell's equations, not isotropic. It has a direction, a polarization. That point source has the model like this, right? This is called a cosine Q. If I had an extra term here called cosine Q of theta, the theta dependence, I could tune with tuning the Q factor. And this is a model, like a mathematical polar model of some radiation pattern, right? Then you could design a feed to emulate that model later on. Or you could have a feed and you can find the cosine Q model that fits the radiation pattern.
So this is an infinitesimal dipole.
Yeah, you can think of it that. Yes, it's exactly like an infinitesimal dipole. That's right. Okay, good. All right, so your program now. So here's your program, right? So you have main reflector here, you have subreflector here, and there are two foci, there's one here and one here, right? And all the parameters are given. So you need two parameterizations. All you had to do in that code that I gave you was to change the parameterization of the aperture plane, which is now a parabola, and the parameterization of the reflecting surface. Point source at this point is still the same as it was in the program. Just those two changes, really. All right? And of course, when you calculate the induced current here, you need 2n cross hi and not just n negative n cross e. Okay, so to do parameterizations, you need a hyperboloid of two sheets. This was given earlier in the notes in this lecture. The parameterization I used is here. And notice that this parameterization for the hyperboloid, which has sine hyperbolic cosine v, sine hyperbolic sine v. Now u is kind of like theta, but it's a little bit different than theta for hyperbolic functions. But v is exactly like phi. So think of v as exactly like phi, and the u, sine hyperbolic u, is some kind of like theta, but it's a little different, right? The hyperbolic angles are different than the spherical angles. Okay, now this has the center between these two hyperboloids at xy equal to 0, z equal to 0, right? What you want is to shift these two parabolas. So here's a cross section of these two, of this hyperboloid, but in the xz plane, all right? And what you want to do is shift these hyperboloid such that one of their foci is at the origin. Here's the origin of this coordinate system, right? Because the points. Okay, so if we want to specialize this parameterization to this figure here, then that means that we're in the xz plane, which means v or phi is 0. So if you set v equal to 0 here, then you get a sine hyperbolic u, a sine hyperbolic u, and then you get this for z. All right. Or no, this part's 0 in that plane, right? Because sine of v goes to 0. All right. So there's a few things here. We need to figure out all these parameters. Here's our parameterization for hyperboloid, but what is a, right? And what are the ranges of u? So this is how you figure that out. So first, we have to shift both these hyperbola such that the focus of one of these, which might be here, is now at the origin, right? So all you have to do is subtract half of the focal length. That's what this does. From the z component, you want to shift them along the z. As soon as you do that, then you'll have one foci at the origin, which is what you want, and the other foci back here. So this is the foci at the origin. Here's x, for example. Here's z. And the other foci is here where the feed goes. And the hyperbola is now in the middle. There's another hyperbola here, but we're not going to use it, right? Okay. Now, we need to find what the a is at the parameterization. How do we do that? Well, we know that the distance from this vertex of the hyperbola to the focus is ss, right? So how do we find, so here's SS, which is the distance from the foci to the vertex of the hyperboloid, right? Okay, but what is this distance? This is the distance along the z-axis. So how do we find that? We say, take the z component of the parameterization and evaluate it at u equal to 0. U equal to 0 puts you at the vertex, right, of the hyperboloid. So here's the z component of the parameterization with u equal to 0. That has to equal to minus SS because this distance here is along the minus z-axis. If you do that, you can solve for A now because this A is the only thing unknown. And A becomes minus SS plus FS over 2. What I'll do is guarantee that SS is the distance between the vertex of the hyperboloid and the focus, right? Okay. Now we need to know what is the range of U in order to give us this distance, the diameter ds, because that's another parameter that has to be satisfied, right? So to do that, we use the x component. So as we vary u, we're going to march along this x-axis if we use the x component till we get to some point here, right? So the x component here tells you what the x coordinate of that parameterization is. So as we increase u, then we're going to evaluate the x coordinate of the hyperboloid. So take the x component, this one, and set it equal to ds over 2, because when u is equal to just the right value, u max, then the z coordinate should give you ds over 2. X coordinate should give you ds over 2, right? Okay, so if you do that, and now you know A, you can solve for u max. U max is this value. So now you know u max, if you want to do the plot of the hyperboloid, u max goes from u goes from minus u max to u max, and v is like phi, goes from 0 to 2 pi. Okay, now what is this theta max? What is the last ray that intersects the hyperboloid? You can find that by using this triangle here, right? For that triangle, we need to find what the z component, or the z coordinate of this tip of the hyperboloid at u max, right? So if I take the z component here, and now I plug in u max, then that'll give me the z component of this tip, because u max brings me to the tip of the hyperboloid, and that gives me the z component, the z coordinate, the z component of the parameterization. So, okay, so we need this point, right? All right, so from the z component, we say that z prime here is this distance. There's an arrow here, there's an arrow here. This coordinate is what I'm calling z prime, all right? But really we need this leg of the triangle, which we're calling z double prime. So z double prime is nothing but fs minus the z prime. So to calculate z prime, we take the z component and we evaluate it at u max. All right. And to calculate z double prime now, we just take the focal length, and we have to add it because z prime ends up being negative, right? You want it less than fs. All right. Once you have those, then you could do theta max is nothing but the inverse tangent of z prime and ds over 2. Right? So that'll fix all your parameterizations for the hyperboloid. Now that we've shifted everything like that, this focus here is the focus of both the hyperbola and the parabola. So that origin should be the focal point of the parabola. So you just draw your parabola. So here's the parameterization for the paraboloid that I used. And in this form here, this is the exact form for the parameterization of a hyperboloid or a paraboloid with a focal length of fp. But this has its vertex at the origin, so you just need to shift it so that its vertex is at minus fp, right? So that's what this minus fp is. All right, that's it. You just add these two to the code, and you literally get this, right? But let me show you one more thing. So, okay, so I'll start here. So this is my code that I wrote. All I did was change those two parameterizations. And of course, how to plot these, you plot these as well. But everything else just ran from what I gave you. So here's the point source at the other foci of this hyperboloid. And all these rays, after they reflect off of this hyperboloid, appear as if they're emanating from the other focus, which is the focus of the parabola, which they better emanate from here, which is the focus of the parabola if you want collimation, right? So that's what the program looks like. And here is the electric field incident on the parabolic surface. I also calculated the current, and I'll show you how to do that. The physical optics current. So to calculate the physical optics current, we need the normal to the paraboloid because we need to do 2n cross hi, right? So the parameterization of a parabola in this coordinate system with z going that way and x going that way, which is different than what we're using. But this, if you parameterize in this coordinate system, the focus of the parabola is here, but the z-axis points to the parabola, where in our problem, the z-axis points away. But this is a well-known normal in this coordinate system, this normal. It's given by this from Balanis' antenna book. We're going to use that, right? So r hat and theta hat in this global coordinate system. But so r hat, all I've done is substitute what r hat is in terms of x, y, and z, and theta hat in terms of x, y, and z components. And then we added up the x to the x, the y to the y, and the z to the z. So you get nx, ny, and nz. But this is in the wrong coordinate system. The z-axis points toward the parabola. We need to negate the y and z components for our coordinate system. So we need to change to this coordinate system. So instead of z going out, we want the z prime. X we're going to leave aligned, which means y has to flip as well to make it right-handed. So y is negated, z is negated, but x stays the same. And then you have your normal. Once you have your normal, you can calculate your physical optics current density as 2n cross hi, where hi, oh shoot, where hi now is nothing but 1 over eta z reflected cross the aperture. And z reflected is the tangent to the ray, the reflected ray, right? Yeah, sure.
So in the code, you computed the normal vector by taking the derivatives of the parameterization and crossing them?
That's right. You take the gradient of the parameterization. That's right. Or yeah, you can do that too. Which is probably
You just have to find the derivatives of the paraboloid parameter.
yeah, that's more like the differential geometry way to do it. It's probably better. Instead of taking the gradient of the oh my gosh. I just put my palm on here and it does that. Okay, so yeah, you could find the tangent vectors here, RU and maybe RV, right? And take the cross product. You gotta make sure it's the right normal though, right? Point back towards the source. Yes.
So do you have to modify the initial conditions from the original code? I don't,
What do you mean initial conditions?
we use VPA solve their initial conditions in there.
Oh yeah, no, I didn't have to. The ones that I put there worked. It should work. This is almost like a sphere, right? So it should give you the right ray. And then this is just it's almost the same problem. That's why it was super easy to give you this as homework. Because of the sphere one was actually probably a little harder. But once you work out all those, then so this is the electric field theta and phi that you get in the aperture, but then you can easily do 2n cross hi of that, right? And yeah. And then, of course, there are standard ways if you go to Balanis' book to calculate the far field pattern due to that current density on that curved surface. You can use a Jacobian to project it back to a circular aperture, and then you just use the integrals in that circular projected aperture, right? It's a really cool program that you wrote. If you end up, this is a cool program. People did research in this, maybe 100 years ago, probably, but this was the only way to do it, right? Before these big computers that we have now. But there are these like big aircraft, right? So military aircraft, hundreds of wavelengths long at radar. And if you want to design like a metasurface for it, then you can use these ray techniques combined with metasurface modeling and just some cool stuff that we're thinking of doing. All right. So it's useful stuff. Okay, so you should be able to do your homework now. My suggestion to you, my advice is to complete your program here because your final will build off of all of this, all right?